Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem named as smallest subset with greater sum. So, in this problem, we are given an array ARR of size n containing non negative integers. That is, it would contain 0 and positive numbers. And the task is to choose the minimum number of elements so that their sum is greater than the sum of the rest of the elements. Suppose there are numbers like 1, 2, 3. So if I take out this 3, then this 3 won't contribute to the sum of rest of the elements. Rest means what is remaining after taking out the element we are considering. Now let us see the sample test case and it would be more clear. So we have 2, 17, 7 and 3. So in this problem, if we take out 17, okay, this is the number we have taken out. So this won't contribute to the sum to the rest of the element. That is, we would have here 2 plus 7 plus 3. That is equals to 12. So if we select one number, then it is sufficient enough to combat the rest of the elements in the given array itself. Okay, so this is what we can do. Now, thinking about this problem, the first brute force approach is that we would start considering the elements. First, we would consider all the one elements, then we would consider the elements in pairs, then we would consider the elements in triplets, okay, and then we would do that. And the first point where this is valid, we would say that yes, this is the answer itself. So, can we optimize it further? Yes, we can optimize it further. So if you look forward, if you want to minimize the number of elements, so if you want to minimize the number of elements, then there would be two kind of sum. One is the elements taken by us, okay, and the next one is element that is remaining, okay, and the elements taken by us should be greater than the elements remaining. This is what they want. Let us see the condition again. Should be greater than this. Okay. So element taken by us and we need to minimize it. Okay. Minimize the number of elements. So we need to minimize the number of elements. So if we want to take less elements with more sum because we need to quickly satisfy this condition. So if we want to take more sum by including less elements, then the best strategy or the greedy strategy would be that we take large numbers. That if we know that we can do it using one number, okay, so taking 2 and then taking 3 is useless at this point of time. So taking 2 and 3 would be useless. So now what we can do is to minimize the number of elements, we would just take the numbers which are more. And that is the crux of the solution. So now what we can do is we can take the largest element. Then we would take the second largest element. Then we would take the third largest element. Okay. So if we want the first largest, second largest, third largest, and the elements are not changing, then instead of finding the first largest, second largest again and again by iterating over the array, the best approach is that we just sort the array. Okay, we just sort it like this. Suppose we would just have 17 at this point, then we have 7, then we have 2, and then we have 3. And then what we can do is we can just count the sum of the whole array. So the sum of the whole array is 12 because we already have it, and then 17 which is equals to 29. So we would have 29. Now what we would do is we have considered 17. So now this side would become 17 and 29 minus 17. What would remain? Is equals to 12. So 12 would remain. Then we would move forward and then we would add 7 to 17 and subtract 12 from 7. Then this value would be, okay, this value would be 17 plus 7 is equals to 24. 17 plus 7 equals to 24. And we have here as 5 itself. And see, you have the value like this. So what we can do is we can find the whole sum and then we can start iterating from the large elements. We would just include large elements, counted, and at this side, this would get shorted down. Okay. So now let us move forward to the implementation and you would have a better understanding of it. Now, what we need to do is we need to calculate the sum. So to store the sum, we would be using int because we need to return an int. Here also give an int and this. But the small thing that you need to notice is that the number of elements is 10 to the power 5 and each element can have the value of 10 to the power 9. So suppose if 10 to the power 5 elements are there and all the elements are 10 to the power 9, that would be 10 to the power 9 multiplied by 10 to the power 5. The bases are same, that is 10 to the power 14, which is greater than 10 to the power 9. So we won't be able to fit this inside an integer. That would be an integer overflow. That is why the best approach would be to move forward with long run. So what we would do is we would have long sum is equals to 0. And then what we would do is for int I is equals to 0, I is less than n and I plus plus. Sum plus is equals to a of I. And here we would just change it to a itself so that we won't have any issue. Okay. Next, what we move forward. Now there are ways to sort the array in the reverse order. The first one is we sort it using a like this. So sort a dot begin and then a dot end itself and then we reverse it. Or else what we can do is we can have r begin and r end. Okay, we can do this. Now we move forward and we would have long res is equals to 0. At this point, we would be having the storage of the left hand side, not on the right hand side. The right hand side is already calculated. So initially we are considering that we are taking all the elements. That means 0 elements is gonna work. Okay. So now what we would do is we would start taking elements. Okay, for int I is equals to 0, I is less than n itself and then I plus plus. And then what we would do is we would add the value of a of I itself. Okay, and then we would subtract the value from the sum. Okay, sum we would subtract. So sum minus is equals to a of I. Here we would add, there we would subtract. Okay. Now, if at any point the value of res becomes greater than the sum, this simply means that the value on the left hand side becomes more than the right hand side. What we would do is we would return the index. But here in this problem, we are told to return one indexing. So that is why we would return I plus 1 because array has 0 indexing, and if we add 1, it would be 1 indexing. At the end, what we would do is we would simply return the value of return. Let us just compile and run and see how many errors are we making. Seems like no errors are being made here. Let us try to submit this and see. And yes, we got an AC. Now let us talk about the time complexity of the solution. So talking about the time complexity of the solution, at each point we are iterating over the array, and for each element we are just using operators. So that is constant operation. So for one element we are doing constant operation. So for n elements we are doing big O of n operation. This is sorting. So this is n log n approach. Okay, this is n log n. And here also we are just using operators. So this is again constant. And this is checking condition. Logical operators also take constant time. So for each element, we are doing constant operation. That is again big O of n. So the upper bound that we have received is big O of n log n. Okay. So this is the time complexity, and the space complexity is big O of 1 because no auxiliary data structure is being used, just the use of variables. That is a small trick that you need to understand, that whenever you are using variables, even if you use thousands of variables, that won't count to the time complex space complexity.